In this video, we'll be looking at slant asymptotes. Specifically, how do we evaluate or find them algebraically given a function? We're going to look at two specific examples. We're going to look at a simple example where it's straightforward in terms of the fact that the power on top is larger than the power on the bottom. Therefore, there is no horizontal asymptote, and we must be able to find a slant asymptote. And then we'll look at one that's a little more complicated, where we're going to have to do some extra work. So for this one here, you'll notice, first off, that the top power is going to be larger than that of the bottom power, and again that implies that there is no horizontal asymptote, but that there is a slant asymptote. Once we know that there's a slant asymptote, if the question is going to ask us to evaluate the slant asymptote, we have to find it. If it's going to ask us to graph the function, if you don't identify the slant asymptotes, that question is going to be wrong because you're going to miss a ton of information by not clearly stating what the slant asymptote is. So, how do we find this slant asymptote? How do we find this y equals function? And it's going to be a function. It's going to be a linear function that's going to guide this function, guide the graph of this function the way that it's supposed to be graphed. So the easiest way to do this problem is by identifying the denominator and the numerator and actually just dividing those two functions as they appear. So we could do this in a couple of different ways. The first way we could do this is by setting this bottom piece equal to 0, have x equals 2, and use our synthetic division method to identify what the slant asymptote is going to be. We could also use long division to do this as well. So in other words, I could go ahead and have x minus 2 sitting outside of a division bar, and I could go ahead and have 2x squared minus 5x plus 7. So a problem like this, again, we could do quite efficiently, but I think it's a heck of a lot more efficient to do it this way. The reason why you need to know that this is a possible method is because there are some really nasty examples that will require that we use this instead. So for this example over here, I'm going to go ahead and just simply write down my coefficients of each term. I'm going to carry down the 2. Just like I'm supposed to do. 2 times 2 is 4, put that here, add these two together, negative 1, multiply those, negative 2, add those together and get a remainder of 5. Now, what's nice about this problem is that the remainder of 5 doesn't actually matter. Let me go ahead and rewrite this function in its divided form. Very much like that when we talked about division algorithm and divided form, the divided form is actually going to show us a heck of a lot of information. So if I go ahead and rewrite this 2x squared minus 5x plus 7 all divided by x minus 2, in its divided form, you're going to see the quotient. That's going to be 2x minus 1. Again, that comes from this here was x squared. Now it's going to be x1, and then minus 1, plus it's going to have a remainder of 5 divided by that quotient x minus, sorry, that divisor x minus 2. And what's going to happen is x gets larger and larger. Well, this thing is going to go off to infinity, but this whole function is going to behave in the way that you would think. It's going to go towards 2x minus 1. Well, this term here, since the 5 on the top is constant, it's not going to increase or decrease in any way, but the bottom's going to get infinitely larger, forcing this whole term to go to 0. So in that case, our slant asymptote will be just the quotient term. Again, y equals 2x minus 1. If you forget to put the y equals in there, then it's going to be wrong. The slant asymptote has to be a function, has to be a linear function, and the linear function is y equals 2x minus 1. So we can show the exact same steps with this. If I were to follow the rules, this is going to be 2x. 2x times 2x is 2x squared. 2x times the negative 2 is minus 4x. And then I'm going to draw the line and then change all the signs. These are going to cancel out. I'm going to have negative 1x left over. I'm going to multiply by a negative 1, and you'll notice once again that the quotient is still 2x minus 1, ends up being the exact same function. This should make sense, okay? This should work out to be the same thing. We're going to still end up with a remainder of 5 when we're all said and done. I'm just going to go ahead and draw a line there and put the 5 down at the bottom because it's not important for me to show this, but it is important for you guys to know how to use that long division. Now, what if we look at a more complicated example? Now, this particular example, g of x, let's call it, equals to, let's do 3x to the, let's do 4th plus 7x to the 3rd minus 2x squared plus 1x plus 1 divided by, and let's do something not terribly complicated, but still complicated enough. Let's do a 5x to the 3rd plus 2, okay? So you'll notice here the only way that we're going to get a slant asymptote, and the only slant asymptotes you'll probably be likely asked in this class, is that the top power is 1 more than the bottom power. It is very unlikely that you'll be asked to find a slant asymptote where the quotient, the remainder, or sorry, the quotient term is going to end up giving you something that's a quadratic or more, because then those aren't really slant asymptotes. Those are really, really unique asymptotic functions. A quadratic asymptote doesn't really make mathematical sense, but it is possible for us to look at it that way. So more than likely, you'll be asked to find the slant asymptote of a function where the power on top and the power on the bottom are only one away from each other. X squared versus x, in this case x to the fourth over x cubed. Now you have to remember that when we're looking at a function that looks like this, you can't use synthetic division. Remember, synthetic division can only be utilized when the denominator is a singular power of x at best. So with this being said, we're going to have to use that long division method to deal with this. And I'm not going to do it outright in its entirety, but I'm going to go ahead through the majority of the steps in how these problems are dealt with to get us to something close to what we need. This is going to be a really, really obnoxious problem with the way that it's going to build out. So the first step that we're going to do is we're going to go ahead and say, what can I multiply this by in order to get this term? Well, I know x has to be in there. There has to be at least one x to make this x to the fourth. And then the 5 has to go away because it's a 3 there, and 5 and 3 don't have any factors in common. So I'm going to multiply by a 1/5 in terms of the 5 in the denominator. That 1/5 then will cancel out this 5, and I need to make it a 3. So 3/5 multiplied by 5 will cancel out that 5 and end up giving me 3x to the fourth. Again, this is a really unique case. It doesn't happen all that often, but I do want you guys to see that division can be an occurrence in some examples. So if I multiply 3 over 5x times this thing right here, I get 3x to the fourth. And then when I multiply 3/5 x times 2, I'm going to get 6/5 just x. So I'm going to go ahead and over here 6/5 x. And then I'm going to draw a line. I'm going to go ahead and change all the signs because it would have been a plus sign here from this plus, but now it's a minus sign. These two terms will cancel out. This stuff will simplify down. It'll end up being something like -1/5 x. And then what I would recommend is I would carry down all the other terms. And the reason why I would carry down all the other terms is because the obnoxiousness of all those terms, it's going to be real easy to misplace something if you don't carry those terms down. And then I have to rinse and repeat with the 5x cubed and the 7x cubed. Okay, so all I'm going to do now is I'm going to do the same thing I did before. The only difference is that I'm going to make it a plus sign. There's no more powers of x that I need, so x to the third is enough. The next piece that I'm going to do is I'm going to go ahead and multiply by the 1/5 again, so a 5 in the denominator, and I'll multiply a 7 on top. Again, the 7 will force the 5 times 7/5. The 5s will cancel out and be left with just 7, and then the x cubed will still be there. So that'll be 7x to the third. When I multiply the 7/5 times 2, I'm going to get 14/5, and that's a constant term, so I'm going to put it over here. Again, I'm going to go ahead and subtract. These terms cancel out. And yes, I can continue to simplify this, but there's really no need to. And this is why I said I'm going to show the majority of the steps, because this stuff here, there's going to be simplification. There's no way to make 5x cubed simplified down into an x squared term. Once the power on the outside is larger than that of the power underneath, we're done doing this division. So in terms of my slant asymptote, again, there is no horizontal asymptote because the power on top is larger than the power on the bottom. My slant asymptote becomes y equals 3/5 x plus 7/5, specifically because this is the quotient, and the quotient linear function will end up being my slant asymptote after doing either the synthetic division for this example or the long division for this example. Again, I would generally avoid long division if you can help it, but sometimes you simply can't. Again, when the powers are larger than 1 on the bottom, you have to use long division, and you can't do the nice, smooth, easy synthetic division.